good morning, good afternoon, everybody, depending on where you're at. Appreciate you tuning in. I'm going to glide over a few of these slides. Some of you, or a lot of you, already know who I am. Again, I work in educational services. I work under Ben Weezer. I've been with the company just since 2017. The majority of my life, I did work out of a truck. I had a high point to my career. I spent about 8.5 years as a service manager for a very large company. I am a licensed journeyman and EPA, obviously, and that's pretty much it for me. Today, we're going to talk about common causes of compressor failure. Due to time restraints, I removed one of these, and that's going to be our slugging, and I'll go over that a little bit with these first two, okay? I'll try to get through this as best as I can for the most part, and I think we'll be close. I've been tweaking it all morning long and last night. But these are in no particular order. We've got refrigerant floodback, got flooded starts, overheating, loss of oil, and debris and contamination. Again, these are in no particular order. If they were in order, as most of you from Emerson know, if not all of you on the phone know, that the number one would be overheating. And the number one reason for overheating is high compression ratio, okay? So the fastest growing one, from what I understand, is this debris or contamination. And I'm just guessing, I don't know to be fact, but I'm assuming it's got to do with all these new things that we put in there, i.e. dyes and different things, flushes. So that falls under that classification. So let's get started here. The way this is set up is we're going to talk about how it happens and then what we can do to fix it, okay? All right, so refrigerant floodback. The thing here when I teach this is the thing that I always point out to everybody. We have two things with the word flood in it, flooded starts and flood back. One is the system running, flood back, and the flooded start is off-cycle migration, okay? So this will be running, the system's running. It's defined as liquid returning to the compressor during the running cycle. Anytime the metering device has lost control of the liquid refrigerant being fed into the evaporator, but more frequently caused by poor airflow across the evaporator. Airflow, airflow, airflow. I don't know how many times you've been out on calls and airflow is the original culprit. Something else might have got damaged, but we can't emphasize enough to make sure your airflow is dialed in. Whenever the load is lost or the liquid refrigerant cannot boil off, obviously, the whole purpose of that boiling off, or one of the purposes is to make sure we're in vapor, particularly superheat vapor. And the whole purpose for superheated vapor, as we know, is to protect our compressor, okay? So the way this is set up is we're going to look at two different types of compressors. The first one's going to be air-cooled. The second one's going to be refrigerant-cooled. Most of our Emerson product is refrigerant-cooled, but we're going to talk about air-cooled also. The reason we do it that way is because if a student is outside tearing a compressor down on day 3 of one of our classes, they have to identify what they're working on because the scarring and the signs of the damage is going to be in different locations. Notice here on the left-hand side, that suction line coming in that head, we'll call this the K-body. The dark blue indicates the refrigerant, liquid refrigerant coming in. The light blue is vapor. So obviously, common sense would tell you once this comes in with liquid refrigerant in here, we're going to get a lot of damage or some scarring up here in between this piston and this cylinder wall. On that note, this is the thinnest film of oil in the whole of this type of compressor, any piston compressor, right between that piston and that cylinder. And then we have the discharge gas obviously coming outside. Something you're going to see on that, if you tore that down, here's like a thumbprint, if you will. I always use that term when we're getting these students ready for day 3, and we call it a thumbprint. It's consistently, almost exactly, fairly close to anyways, of what this looks like consistently. And what's happened here is this has washed away the lubrite. This is a cast iron piston. These are oil grooves in this piston, and you can see how this has lost its color there. That's coated in lubrite, and solvent or POE oil refrigerant acts as a solvent. So this has washed away the lubricity and caused that to cause a little friction there, okay? Now, on a refrigerant-cooled compressor, we have the refrigerant, liquid refrigerant is going to be indicated in the blue, okay? So the gas would come in. Typically, it would impinge on that stainless steel mesh filter screen and drop down. In this case, the liquid refrigerant is going to go down. The vapor refrigerant is going to go up through the throat. The liquid refrigerant is heavier than the oil being the color yellow here. So there's a pickup tube right here, picking up that oil, thinking that it's oil, but it's actually liquid refrigerant, coming up to the shaft, working its way down to the bearings and the journals there. And the further it gets away, the worse lubricity or oil that we have. And we call those markings progressive wear. Okay, so again, it's like a thumbprint, and this is very consistent in our teardowns. You'll see less damage here because we had a little bit more oil right here mixed in with the liquid refrigerant. As it got further away, we've got more and more damage, the scarring, and we call this progressive wear. And you'll see why I'm calling that, we call it progressive wear, because there's going to be 3 different markings or thumbprints, if you will, on these shafts. Notice this scarring. This is actually a bearing that's actually pressed into the compressor itself. It shouldn't be on that shaft. So a lot of times when we get compressors back on the teardown, whether they're under warranty and maybe we've lost 1 or 2 on the same job, what you and I, or what contractors see out there, is typically marked as they take their voltmeter out and they see it as an electrical issue. But what we find when we tear them down is very interesting. I learned a lot about this since I've been here, is more times than not, it's a mechanical issue that led into an electrical issue. And these are a couple good slides that point that out very well. See the scarring on the rotor here? I want to back up a little bit just for a second here. So this bearing, this is all wearing down, and these bearings are becoming loose. I'm going to use the term sloppy, if you will. The weight of this motor starts to hang down as it continuously runs on. You've seen the wearing here. You've seen the bearing here. We're going to start to wear down and get some slop in there. It's going to start to sag from the weight of that rotor on there. And as it starts to sag, it gets close enough to this stator here, and it arcs out. Boom. Contractor comes up to the compressor. It's not running. Takes his voltmeter out. Calls your shop and say, hey, I need a new compressor. I've got an electrical issue. It may or may not get tagged, but if it does get tagged, that's what they're going to write down 9 times out of 10. But it started out as a mechanical issue, liquid floodback in this case. Okay, so some of the causes of liquid refrigerant floodback: inadequate airflow, blocked dirty filters, closed grills, dirty fan blades, fan motor failures, poor heat transfer, recirculation of air, product location, that's a big one, overcharged on a fixed metering device, overcharged on a thermostatic expansion valve system may not cause liquid refrigerant floodback. Why? Because that bulb is on the back side of that evaporator, and it's modulating that, if you will, opening and closing that so it can sense that liquid refrigerant coming in. Misadjusted or malfunctioning TXV, maybe it's sized for the evaporator load. Bulb installation, that's a big one. And cleanliness of tube. External equalizer, foreign material possibly. Superheat setting, is it too high? Is it too low? Sudden changes in the load, hot gas or reverse cycle defrost, heat reclaim or reheat, possibly a condenser fan that's cycling on and off. We got low ambient or something like of that nature, and then the evaporator fan switch. So how are we going to prevent refrigerant floodback? And I know you're all screaming at me right now. This is typically, as Ed and Ed were doing the other day, going, this is typically when we ask the class this question, and that's where I would lead into them. But since we're doing this the way we are, I'll just tell you. So the first thing that comes to my mind, if we don't want liquid refrigerant coming back in the compressor, we would want to check our superheat entering the compressor, okay? So I always tell students just to start working backwards. Where is it happening at? Refrigerant liquid floodback, properly selected components. We need expansion valve sizing. Check the expansion valve sizing. Do we have proper airflow? Air distribution, the refrigerant charge, and we'll show some AE bulletins on that here in a little bit. Check for sudden changes in the load, okay? And do we have a suction accumulator, or do we need a suction accumulator? That's something to think about. And install a suction to liquid line heat exchanger, if you've seen those, okay? So here's an illustration of a superheat on systems where floodback has been a problem and other solutions have failed to resolve. Emerson is going to recommend a minimum superheat is 20 degrees at high load condition. And notice that says high load condition. So what we're saying there is we want in the peak of the day, let's pretend it's 1 o'clock in the afternoon, the supermarket's really cranking people in and out. maybe it's a holiday weekend, 4th of July, all the doors on the coolers are opening up, so we're in a high load condition. Why? Because we lose more compressors on low load conditions than we do on high load conditions. And what we're saying by that is if we know we have 20 degrees superheat at the compressor in high load conditions, we know in low load conditions, maybe when it cools off at night, a big temperature swing in some states, it will at least have something at the compressor. It might only be 4 degrees, but it's something to protect the compressor. And this just shows you the formula, obviously, that we all know. We do recommend that you take that reading within 6 inches of our pressures, if at all possible, okay? I did put this bulletin in this morning. If you go, this is one of probably a couple of them that are out there that refer back to this, but you can go to AE17-1362. It'll tell you all about that, okay? Now, let's move on to flooded starts. Again, flood back was running. Flooded starts is off-cycle migration, okay? So at my house here in Ohio, my furnace is, I've got a natural gas furnace. I'm heating up my A coil on the top of my furnace. It's an upflow furnace. I'm heating up that vapor, and the refrigerant is like me. It's looking for somewhere cold to go. Hot always goes to cold. High pressure goes to low pressure. But that vapor refrigerant is looking for some place to snuggle, and depending on the length of my line set, 15 foot, 20 foot, or the size of the line set, or the delta T difference from outside to in, the faster that refrigerant is going to go out there. So there's a lot of variances there. Length of time that it's off. But once it goes in and the vapor gets into that oil down the compressor, it wants to cool off naturally. It then condenses and raises the level of that oil, and you have the refrigerant, liquid refrigerant, and oil mixed together. Okay, refrigerant migration occurs anytime the refrigerant and oil are in contact with each other, and the compressor is not operating. Again, off cycle. Liquid refrigerant in the evaporator vaporizes and moves to the crankcase as a vapor. Refrigerant vapor in the crankcase condenses and absorbed by the oil. This is a common problem with refrigerant-cooled compressors only, okay? Flooded start, notice the illustration on the left-hand side. Notice the refrigerant coming in. Again, the oil rises. It turns into spring. I'll just use my house as an example. It's for easy explanation. I don't bump start it in the spring of the year. My wife sees it's getting warm. It's that odd first warm day. She turns it on. We get this explosion of refrigerant. That refrigerant wants to boil off inside that compressor, and we start breaking things. That's where we get the reference of slugging. Anytime we got liquid refrigerant in our compressor, and we start to see broken parts. Now, this thumbprint, if you will, on the shaft is going to be what we call good, bad, good. By the physics of the way that the compressor is made with this dividing wall here from the motor and the crankcase here, it has a natural instinct to want to go right up here and kind of come to a point. So we refer to that as good, bad, good. You'd be amazed how many times in the short time I've been here that we pull them out of the compressors identically to this. I mean, it's again, I know most of you from Emerson with all the years of experience you have know this already, but it is truly like a thumbprint. It's very, very amazing. But this is what happens. That refrigerant runs up that dividing wall and breaks parts or scars that shaft the way it is, okay? How are we going to prevent that? And again, I know you're all screaming here and you know this already. Most of this is just a refresher for you. Well, if hot wants to go to cold, we want to, for one thing, we definitely want to heat that compressor up. So we would look at possibly changing a few things out there. The length of the compressor off time is going to affect it. The compressor ambient temperature, or the delta T from outside to inside, the temperature difference between saturated refrigerant and the evaporator and the oil in the compressor, and last but not least, the refrigerant charge to oil charge ratio. And again, we put a AE bulletin there that explains that 80-20 to you, and I'll make sure you're not overcharged on that, okay? These are just some examples of some crankcase heaters. This is the probe type. This is the bar type for the semi-hermetics. This is probably the most, the common one that we see, okay, this belly band or this wraparound type. The whole idea, again, is just to trickle some volts through there and keep it warm when it's off cycle. An off cycle could be a season, like I explained to you, and an off cycle could be just hours. It could be 5, 6 hours, 4 hours. If there's a big temperature swing, you can still have off cycle migration, okay? This is what we call a continuous pump down, seen more on the commercial, on the supermarkets and what have you. You wouldn't see this in residential. And the way this works is we have a thermostat up here, okay? We have a normally closed solenoid valve here, identified by the S. We've got the box temperature, let's say at 35, just for the sake of not arguing, and it hits 36. It activates, sends power to the head here, opens our solenoid up. Refrigerant goes through our TXV, comes around through the evaporator, past our bulb, past our P, which is the pressure, low cut pressure cutout, through the compressor, back through the dark red here, and into the lighter red. And this is our condenser, obviously, and then our storage vessel, or our receiver, okay? And it comes on through all the way through the cycle. The thermostat then satisfies, okay? The solenoid shuts down, normally closed, okay? But the compressor keeps running, okay? And it keeps pumping down. Now, the reason we have this low pressure cutout down here, and I'm just gonna throw some numbers out there, we're gonna say that we're gonna cut this out at 20. The differential is gonna be 10. We're gonna cut back in at 30. And don't hold these numbers to any, and they're not sketched in stone. I'm just giving some examples, okay? So the compressor keeps pumping down and keeps pumping down. Even though the solenoid is closed, we get it back here to the condenser and into the receiver. This hits the 20 cutout and shuts everything off. This gets 1 degree warmer. Our set point gets a little higher from what it's set. It turns back on. We start the cycle back over, okay? And then we pressurize. Once we hit that 30 to cut in again, the compressor starts back up and the whole cycle starts up again. The whole purpose is we're moving that refrigerant back here where it can't migrate back to our compressor, okay? Let's talk about slugging a little bit. Slugging is nothing more than, I always refer to it as like a bullet. It's a liquid bullet in our vapor pump, okay? Whenever we see broken parts, I tell the students or the technicians, write it down. It's part of your story. You took a slug. And there may be other issues, but you for sure took a slug, okay? Causes of slugging on air-cooled compressors usually results from floodback. On refrigerant-cooled compressors, it usually results from migration, and that's key to know that, and that's why when we're teaching other contractors and what have you, or other trainers, we emphasize you need to know what you're working on. Use Copeland Mobile, and we ask them to use the Copeland Mobile and identify what you're working on. When was it made? What year was it made? Is it air-cooled or refrigerant-cooled? And that'll tell you a lot about the compressor before you start. So here's these wrist pins. You have an aluminum connecting rod, a steel, wrist pin here, and then you have the cast iron piston here. So what's going to give out first, obviously, is this aluminum connecting rod, okay? And we get that liquid refrigerant here. This is that clacking that technicians or service guys hear when they go to the roof of a system and they hear that clack, clack, clack. A lot of times what we'll have students do is take that piston in one hand and the end of this journal here and pop it real quick. If they hear some slop in there, that adds to their story, what they're going to tell us on day 3. Now it looks like that we've got some play here. As we can see. And I only put a few pictures in here, but this just shows you a scroll. This is the bottom scroll section that's referred to as the orbiting scroll. This is the fixed scroll. This is actually upside down. This should be setting on top of here. This actually has flanks and tips just like this does. Obviously that broke all the way off. So even as good as our scroll compressors on, at one point, they're going to bust some parts, okay? They'll tolerate a little bit, but not that much. Overheating, the #1 killer of compressors by far, okay? Overheating, let's talk about overheating. Causes of overheating, high compression ratio, okay? Head pressure is too high, or the suction pressure is too low, or maybe both of them are low and high. High return gas temperature coming back to the compressor, okay? Maybe it's too high. Where did it start at? Maybe, it might be back as far as the TXV. Maybe it's not letting enough refrigerant in. And a lack of external cooling, and I have an AE bulletin down here. We're talking about our air-cooled and some refrigerant-cooled that have a fan on top of them that blow 1,000 CFMs to them. Overheating, This is just showing the hottest point of that compressor at the discharge point internally, okay, and that'll be key here in a little bit. Key facts about oil temperatures: at or around 300 to 320 degrees, it causes ring and cylinder wear. We also start to cook that oil, okay, and that's important to understand that. It breaks down at 350. In fact, it starts to carbon, okay, and creates contaminants and accelerator wear, okay. This is just an example of what that looks like. You can see the valve cover here. You can see how somebody ran their thumbprint over there and knocked off that tarnish. These are cantilever backers, the sole purpose to support that stainless steel reed valve there. You can see how the indentation there, how hot that got. So this got pretty hot. I kept this one in there because I think it's a nice slide. You notice the discolorization, the blue here, and we all know what that means. That got very hot. Again, this is the fixed scroll at the top of this scroll compressor. What are we going to do about overheating? What can we do? Causes of low suction pressure and high condensing pressure. High condensing pressure, again, this is based on compression ratio. Well, some of the reasons for that could be blocked, dirty condenser, a recirculation of the condenser air, erratic condenser fan operation, possibly a bad cap maybe, overcharged of refrigerant, or maybe we have non-condensables in the system, or maybe it's an undersized condenser. What's the possibility of the low suction pressures? Wrong sizing of the components. Maybe our metering device is misadjusted, or a loss of refrigerant charge, plug dryers, strainers, and suction line pressure drop. I know Ed and the guys were talking the other day about how important it was in sizing that refrigerant line, and it is. And this is an AE bulletin number here. This just shows you an illustration of an uninsulated suction line coming back, picking up that heat, okay, and bringing up more heat, more superheat back to the compressor. This is showing you an example of possibly being in an unconditioned space, possibly in an attic with no insulation in there. I like this slide because it gets guys and gals like myself to think about things like that and think about the importance, because when you're just starting out, especially, or if you had only on-the-job training and didn't have the luxury of going to school, those kind of things are important to teach. Here's an AE bulletin that I put in there this morning to look at. And this is a critical internal temperature. Again, I have an AE bulletin. We often teach on the semi-hermetics and some, if not most, of the scrolls. We can't say all of them. The cylinder wall temperature must be below 300 degrees. And we always teach that we don't want this, we would like this not to be higher than 225 degrees. We commonly say 225, stay alive. And where that derives from is we found over the years that we lose somewhere between 50 to 75 degrees temperature from the hottest point of this compressor. So going with the worst scenario of 75 and adding it to 225 without getting inside the compressor with a temperature probe, we can tell pretty accurately what the temperature of that compressor is inside 6 inches down the discharge line on this semi-hermetic. 225, add 75 is 300, that magical number where oil starts to break down and things start to cook. It's a nice little way to add something to your tool belt. If you know what the temperature going in the compressor is, and you know what the temperature is on the discharge line, you just told yourself a lot about that compressor internally without opening it up. And that's a big eye-opener to a lot of young technicians.
Don, I'm glad you just said that, because we just had a question come in asking this was a minute or two ago, asking what temperature should the discharge line never exceed. So thank you for covering that.
Yeah, and then it will, on some of it, and we won't really deep dive into that today. Some of it's going to have thermostats on exterior that's going to cut off around 260 or 270. The difference is over 225, we're outside the envelope. We don't shut you down. On an outside external thermostat, we're going to shut you down at 260 or 270 because we know you're cooking. 225, it may run hot a little bit, but we always tell everyone, in order for it to get that 15 years expected life that we shoot for on the average, we don't want that to run outside the envelope, and that 225. So very good. Loss of oil. Loss of oil. Oil leaving the compressor must equal the oil returning the compressor, okay? This just shows, again, some seized bearings. Again, look at the fingerprint or the thumbprint on this shaft. We had progressive, we had good, bad, good, and now we have just a common all the way down dark colored markings from loss of oil. Again, this is like a thumbprint. I know a lot of you on the line from Emerson. I know how much I've seen a lot of the names that are on here and all the years of experience that are on here. I know a lot of you do tear down. I've seen some of your videos. Just a tremendous, great job. But these are seized bearings that shouldn't be on that shaft. Again, they should be pressed into the core of that compressor, okay? This is the bottom. This is the lower bearing of the scroll compressor, which should be, I say, submerged in oil at all times. And you can obviously see that was not. Okay, you see the scarring inside there. So that was cooking pretty good. A lot of friction. So what are we going to do about loss of oil? A tripped oil pressure switch is a warning sign of trouble. Before the oil pressure switch is reset, look at the compressor sight glass and record that oil level. Can't emphasize that enough. Never, never, never let the manager or the store owner see you press that button and reset it, okay? There is a reason, and you need to investigate that. No oil is visible in the sight glass, that's a problem. Oil level is in the sight glass, to me, that's a bigger problem. You can see the core sense on there, okay, detecting that. Okay, so here we have an example of a pressurized crankcase, okay? So we had a service call, and when we got there, the oil was in the sight glass, and we're scratching our head, and we're wondering what happened there. Probably just a bad core sense. We did have a thunderstorm come through last night. As a contractor or a technician, you're trying to make yourself believe anything you can to get on down to the road to the next call. Believe me, I've been there before. So what's happened here is if you run into that situation, or a technician does, what we're going to ask you to do to rule out the possible blow-by, when you get loss of oil, remember that thin wall, the thinnest wall of oil, film of oil we talked about right here? When we get loss of oil, that starts to get heated up pretty good, and it starts to, for lack of better words, bore it out, if you will. Okay, that piston starts to rub up against that cylinder wall, and you start to get blow-by, okay? So what happens is this is a normally open check valve, and the only time that should close is on startup, okay? So it's a normally open check valve, and this is designed about 2 pounds less in pressure, lower pressure than this side, because high pressure wants to go to low pressure, right? So that oil comes down here, goes through the normally open check valve, comes up through here, picked up through the tube, and down through the shaft, and everything's good, okay? When we start to get that oil loss there, we start to get that blow-by, our less pressurized side of our crankcase, 2 pounds, 3 pounds, 4 pounds, whatever that looks like, starts to pressurize. This vent, by the way, is put in here to keep that pressure lower on this side. When that vapor comes across this motor and cools it, it comes across this throat and comes across that vent, if you will, and almost causes like a Venturi effect. Think about sucking on a straw as it passes over there. So it's always keeping this pressure lower. Unfortunately, when we get this start to go by here, this ring wear, we get that blow-by, this starts to pressurize. And what happens next? Our normally open check valve closes. The oil still is coming down because it doesn't know any better, and it stops and starts filling up here. Meanwhile, the compressor's still running, so it's still picking up oil through the pickup tube, and all of a sudden our core sense goes off, showing lack of oil because this is closed. All of a sudden the system shuts off. This part of the crankcase pressurized increases, it depressurizes. This opens up, the oil goes back to norm, fills that sight glass halfway up where we like it, and Don comes out to look at the compressor, and I'm scratching my head because the oil's back in there, and but it was tripped off on low oil. So what we want you to do is we want you to hook your gauges up right here at the suction line, okay, right before entering the compressor on this refrigerant cooled. There's a plug on the side of this compressor. We're going to ask you to remove that plug and put a brass fitting in. It's like a 1/2 by 1/2. You'll have like a flared fitting on there on the one end for your refrigerant hoses. So you're hooking up a refrigerant hose here and your refrigerant hose here. Shut the suction valve off coming into the compressor. we want you to turn this on. What you should see is, if there's no blow-by, is your gauges will both go down at the same time and be fairly close to each other and bottom out. If for some reason there is blow-by here, the gauge, that the hose that this is connected on, will start to go down, and then somewhere before it gets about halfway, it's going to stop while this side continues to go down. And that will let you know that you have a blow-by or a pressurized crankcase here. This cannot be repaired, by the way. But if you get a problem child like that, it's something to look at. Very, very hard to figure out, by the way. Okay? Cause of loss of oil, poor piping. Ed and the guys talked about this the other day. I removed a lot of the trapping pictures in here because they nailed it so well the other day. Improper traps, inadequate defrost, loss of charge, possible short cycling. What does that mean to me? Short cycling, turning on and off a lot, not getting that oil returned back from maybe the evaporator, so it's stuck out in the system somewhere there. Okay, low load conditions. Again, low load conditions. Okay, on rack systems, you may have a plugged oil filter. That's a big one. Okay, this is just an illustration of a P-trap. If you choose to make your own P-traps and you don't buy the P-traps, we're going to ask you never to go 4 times the radius of the size of the refrigerant line. So whatever this refrigerant line is, diameter, the OD, never go 4 times larger from outside to outside there. Okay, that keeps good turbulence up through that P-trap, as Ed was explaining to you the other day about that oil not running back. Okay, so never more than 4 times the radius from outside to outside of the size of the refrigerant line. Okay. This is just showing you, this is one of the few that I kept in here. Just want to let you know that we're going to ask you to have about a 1/2 inch, 1/4 inch, whatever that looks like to you, every 10 linear feet going back in the direction of the refrigerant, okay? We're also going to ask you to trap 20 feet before the riser, have a trap at the bottom, and then go and trap again at the 20-foot mark. And again, we want you to pitch that 1/2 inch, 1/4 inch, every 10 linear feet, okay? We're going to talk about inverter traps. Actually, I didn't, I removed that. But Ed talked about it the other day. If for some reason this was coming in, it wasn't at the end like this, where we know we have a 1/2 inch fall, we would have this inverted, right? We would have inverted coming in the top of this header, and so it couldn't come back to the evaporator on shutoff. Now let's talk about contamination, okay? I just saw a question come through, Julie. Did you see that?
I did, yes. Does the trap distance stay the same on variable speed compressors?
That's a good question. You know, I've never been asked that. Does anyone from Emerson or anyone know that answer? I do not. I'm not sure.
Ooh. Let me, I'll tell you what, keep going, and I'm going to look through all of the Emerson people that are on. And if any of the Emerson people want to answer that question, or any of the customers that might know the answer, feel free to drop your name in there. Does the trap distance stay the same on variable speed compressors? Maybe there's a t-shirt or something in it for you.
Yeah, there you go. Great question, by the way. Very good. So again, we talked about the fall. Let's go into contamination. Okay. Contamination, again, this is the fastest, largest growing piece of the pie, if you will. See a lot of die out there. I would say right now, if we tear down 10 compressors or 20 compressors, I would almost bet you that about 60 to 70% have die in them. Obviously, when we get die in there, you know how PT charts work. We can check the PT charts up against a recovery tank. You know how that works with the, as long as we have vapor and liquid. Well, you can imagine how that's throwing that off if you start putting so much dye. And even in the short time I've been here, I've seen it to where we've poured refrigerant out of these compressors that's come back to where it fills up a 5-gallon bucket or about a third of the way up, and it looks like radiator fluid. It's really, really bad out there. I'm sure the folks that are in the wholesale business understand that better than I do. I like this. This is one of my favorite slides when I'm presenting this section. So this is a nice a slide here, and what this is moisture. This is from pore evacuation, and we're going to talk about this next week if Julie wants to. This is moisture inside the system, okay, and high heat, and we call this copper plating, okay? But what I really like about this slide is here, obviously they didn't pull down to 500 microns or less. We always teach the students what this serial number says. The first two are the year that it was made. The letter here is the month. So we're looking at January 2012. And look at this, how when this compressor came back July 5th of 2012. So that was a very short time that it was out there in the field. And obviously it was in transportation. But it gets better, because by this time in the class on the third day, we've taught them what bill of materials mean. And this is an 800 bill of materials. So somebody out there is just changing compressors, you know, and I know all of you, if not most of you, if not all of you, know this as well as I do, that a lot of times, or most of the times, and obviously I'm a little biased for Emerson, but it's a system problem and not a compressor problem, okay? Let's talk about motor failures. And I always emphasize, too, on that copper plating, that moisture. A lot of these things that happen are just things that I or the other service technicians did wrong on the initial installation. What we don't understand in the field sometimes, if we don't get enough training like the Copeland classes and different wholesaler classes, is what I do today affects the system, maybe not tomorrow. It may not show its ugly head for a year or two or maybe 5 years down the road, but it will show its ugly head up. That moisture is very acidic, just like other things that are acidic. Flux is acidic, and it starts to eat away that copper in those refrigerant lines. So everything it touches turns to copper plating. And I pulled these out before the shaft's out, and students have taken them with them when they're not under warranty in Sydney, and they look like a penny. I mean, they're so bad. But so the technician shows
so,
that
hey,
5 years.
Don,
yeah.
Don,
yeah.
We do have an answer. Paul Cucino posed out there, maybe you need double risers, and Ed Sethens validated, yes, use a double riser on systems with capacity control, either variable speed or digital. So
that is great. That's great.
It.
Yeah, no, and I think Ed even touched on that the other day at full capacity. Very good. Yes.
Any form of capacity control that has lower velocity, especially if the capacity drops below 40%. So
okay.
Thank you, Dave Dowen, Paul Catrino, and Ed Sethens.
Thank you, guys. Appreciate it very much. Thank you so much. Okay, let's talk about motor failures. Motor failures. A single phase, we're going to have a general burn is the issue. The description of that is the entire windings burn. If you've tore down a compressor before, you'll know that the students tearing one of these down, they stink like all get out. I can smell them from a long ways away. The spot burn is just a localized burn. A start winding burn, only start windings are burned and then leads are shorted. Down in the three-phase area, the issue would be half winding burn. Half of each winding is burned. The single phase is a two-phase burn, and the primary single-phase burn is one-phase burn, okay? This is a general burn, and again, I can almost smell this through the screen as much as I've been around these since I've been here. So many teardown classes, and and I'm sure a couple of you are giggling about it, but as many teardowns as I see you all doing. This is a general burn, obviously very, very contaminated, and you can see the damage that's done there. Heavy stench on that. This is a spot burn. This could be something as simple as someone using a Sawzall cutting their copper lines on the initial installation. Maybe a piece of copper flake got in there and laid across these windings there, and it got warm and burnt that off there, and now we have a spot burn. Again, back to that initial installation, how important that is. Contamination. What are we going to do about contamination? Well, we'll start with a sight glass. This is your liquid line filter glasses, okay? These are the sight glasses. I think the industry standard is no more than, I believe it's 100. Most of these are set for 75 parts per million. This one, I know, I feel confident in saying it's 50 parts per million. But we always emphasize we don't want this to get too wet before we change the liquid line filter dryer. We're going to suggest as soon as it starts to move into the caution area, the things you're going to see in that sight glass, okay, discolorization. We used to do a lot with these with bubbles, but since the blends have come in, we don't really, we don't always hang our hat on that, if you will, but definitely moisture. This is what we refer to as the window to the system. We want to change a filter dryer, liquid line filter dryer, whenever, okay, ever the system is open for service. Anytime the system is open, we change the liquid line filter dryer. When the pressure and temperature drops become excessive, or when the sight glass shows excessive moisture. Just a fun fact that I learned since I've been here from some of my mentors. Actually, everyone's my mentor here. I'm still a sponge learning all this, but I guess years ago they bought, Copeland or Emerson bought as many of these liquid line filter dryers as they could at everybody's brand. And what they found was out of the box, you typically have a 1.5 pound, 2 pound drop on a brand new liquid line filter dryer. So we always encourage the technicians or the contractors to take that 1.5, 2 pound nominal drop in consideration if you're replacing them after a 2 or 3 pound drop across there. You're going to have to add that 1.5, 2 pounds across there. And obviously, if you don't have the luxury of taking those pressures on each side of it, we'll deal with temperatures then. Anytime you see ice on any side of it, obviously that needs to be changed. It's a no-brainer, right? Clean up on the suction side, acid removal. Oh, by the way, liquid line filter dryers, as most of you know, 3/4 of it is liquid molecular sieve that is removing moisture. 25% of it's for acidic. On the suction dryers, it's flip-flop, completely opposite. Primarily for acid removal, we're going to ask you to leave this in on the suction dryer no longer than 48 to 72 hours. It needs to be removed. If you test the oil or take an acid detection test and it's still not cleaned up, we need to get this out, put a new one in, and start the process all over, okay? We do not leave these type of suction dryers in the system. Again, going back to what Ed talked about the other day on that pressure drop, okay, going across there. Very, very plays a heavy effect on our compression ratio. That suction is really weighs a lot on the capacity of our compressors. I guess I made it. I'm surprised. I shouldn't have removed as much as I did. Is there any questions? And I appreciate the help that we've had today.
So we have Randy Tebby has now weighed in and said this is the double riser is not always the case with digital scroll, because when the digital, actually, you know what, Randy, if you're out there, I'm just going to unmute you because I'm just reading what you're saying, and I would rather you just speak to it if you're out here.
Please.
Okay, can you hear me?
I can hear you. Good.
Okay, good.
Go ahead, Randy.
And again, this is a discussion that I think Ed Seffens is also weighing in on. But when we look at a digital scroll, when that compressor is pumping, it's pumping at 100% flow rate. So it's going to have the max velocity through the lines when it's pumping at 100, when it is pumping or when it's loaded. And when it's unloaded, it pumps at 0. So whenever it is running at full flow. So it's not like it has reduced flow rate through your suction lines.
Gotcha. Very good. That makes sense. That's awesome. Thanks, Randy. I appreciate that.